Well, good afternoon, good morning, whatever it is for you. Hope everybody's doing well. Today, we are going to be discussing functions and relations. So a lot of this stuff should be fairly straightforward. At least the stuff today is not going to be as wildly varied as it was last week. But first we got to talk about, what is a function or even what's a relation. So let's go ahead and start there. So simply put, a relation is a collection of ordered pairs. And so what that could look like is that could be anything from, here is a graph, which is made up of an infinite number of ordered pairs. Or it could be that I give you a finite set of ordered pairs, so something like -3, 2, 5, 0, 0, 2, -6, 1, and -3, +3. So you're using those curly brackets there. It means that's set notation. And so for the second example, it's just these 5 ordered pairs, right? That's all it means to be a relation. And we use relations a lot of times to connect two different pieces of information or data. So it might be that the first ordered pair, or the first coordinate of the ordered pair is, say, somebody's student ID number, and then the second piece is going to be their name, right? So it's a relation. You have two pieces of information that are somehow tied together. Well, when it comes to all of this stuff, we want to talk about two big things. One of those is going to be the domain. And so the domain will be the set of x values, used in the relation. And then the range, will be the set of y values used in the relation. That's all it is. So the domain is going to be the set of x's. The range is going to be the set of y values. That's it. So if we were to look at the example that I have up here, this graph, and I'm going to tend to do this. I think this might be helpful. I'm going to do domain in blue, and I'm going to do range in pink, as long as I remember that's what I'm saying right now. So when I look at the range, if you look at this graph, the little wavy guy, you see that in terms of the x values, he's going all the way to the left and all the way to the right. Hold on. And so for this one, we would say that the domain is all real numbers. If you look at the x and the y axes as though they are number lines, you think about, what am I including? And you see what I have shaded there in blue, and I'm including everything, right? And you would see something very similar happen when it comes to, I wish I could change the way that looks. Oh, so you see with the y, this guy is going all the way down. He's going all the way up. And so if you had to, map all of this to the y-axis, you'd have to include everything. He goes all the way down, and he goes all the way up, and there's no break, there's no gap there. So then when we talk about the range, we would say this is also going from -infinity to infinity. It's as simple as that. And because we have a graph that is continuous, we're going to be using this interval notation because we can't list the infinite number of points that make up this picture. So as I go from left to right, there are an infinite number of points making up the graph. And so you can't say, oh, these are the specific x values that I'm using. So you have to use the interval notation to describe that. Now, for this second example, just scroll down here. Actually, I'm going to... Oh, you got weird on me, didn't you? Let's move that down just a little bit. All right. So here, when I want to talk about the domain, for the second one, I'm going to use the curly brackets, the braces, to list all of the x values that are being used by this relation. So you see that we're using -3, 5, 0, -6, -3. Now, I'm the kind of person who tends to want to put these in order from least to greatest. So I would list this as -6, -3, 0, and then 5. And you might say, well, don't you have -3 there twice? I do, but you don't need to say that you're using it twice. If you are listing it as part of the domain, you are saying, hey, I need to use this in my relation. And that's fine. You only have to say that you're using it. You don't have to say how often you're using it. And then when I look at my range will be the set of y values. So I'm going to pick off these y coordinates that we see right here. And if I go from least to greatest, that is simply 0, 1, 2, and 3. And when we use this set notation and we are listing these specific values, these are the only values that we're using. So for the range, when I say 0, 1, 2, 3, these are the only 4 values that I'm using for the y. Nothing else. Okay, so that's domain versus range. Now, the big topic for what we're talking about today is the concept of functions. And what is a function? So a function is a relation. So it is a collection of ordered pairs, but it's a relation in which each value from the domain is paired with only one value from the range. So it is a relation where each value from the domain is paired with only one value from the range. That's it. And a way to think about this is that if we look at our domain versus our range, we can think about this maybe in some slightly different words. If I talk about the domain, I typically talk about this as your input value and your range as your output value. And so if we think about what that means in terms of this definition of a function, that means that for a relation to be a function, each input gives you exactly one output, nothing more. And that's kind of what makes the world go round a lot of times. If you type a certain calculation into your calculator, you expect there to be just one answer, not multiple answers. If I were to go to my college's system and I were to search for a student by their student ID, there should only be one student that shows up with that ID. Because if you have multiple students with that same ID, things get confusing. It's like, okay, well, which student actually took college algebra? Which one took English 1301? Or if you were to look at, say, social security numbers. The social security number, if you type that in, if you did a search for it, there should only be one person who is connected to that. Should be. All right, so with this in mind, if we go back up here to the top, how can we determine if we have a function or not? Well, if we look at this collection of ordered pairs, is each number here in my domain paired up with just one value in the range? And if you look closely, you'll see that we have a bit of an issue going on here. We see that we have -3 is paired up with 2. In other words, I plug in -3, I'm getting out 2. But you also see over here that if you plug in -3, you're getting a different answer. So that means that this guy right here is not a function. Because in order for it to be a function, each value you plug in, each input, each x, can only point to a single y value. Now, what about the graph that I did up above? How can I determine from a graph whether or not this is a function? Things get kind of difficult, unless you know one little trick. And that is something called the vertical line test. So this is used for when you have a graph and you're trying to determine, is this a function or not? So vertical line test says that a graph represents a function if every vertical line crosses it in at most one point. So if every vertical line crosses your graph in at most one point, then you're talking about having a function. So if I look back up here and I were to try to do this vertical line test, no matter where I put a vertical line, if I put it here or here or here, you see that you're only crossing the graph in one point. So no matter where I draw a vertical line, I'm only ever touching the graph that I've drawn, in one point. So this graph is a function. And so what we want to look at now is this. I'm going to go through a series of graphs, and we're going to determine the domain and range, and then figure out is it a function or not. Now all these guys are going to be relations because they're graphs, but determining whether or not we have a function is going to be a slightly different story. See, menu, your exams are finally over. Huzzah, hopefully everything went well for you. I just finished grading my exams today. See, nobody ever thinks about the teacher. Nobody thinks about, oh, they have to actually grade my work. Yeah, that's what I did today. I wanted to sleep, but I did my work. All right, so I've got this in the wrong. Hold on a second. Hold the phone. What have I done? There we go. All right, so let me... Wait a minute. Okay, let me do this. Come back over here. I'm going to put a graph up here. And... Boy, I feel like I kind of got to make some room here. Let's make this a little bit smaller so we can actually see it better. All right. So let's take this graph right here. Does this represent a function? Well, I hope that we can see that this does not represent a function. And the reason we know it doesn't represent a function is because if I were to take a vertical line, well, if I do a vertical line over here, that doesn't cross through the graph. That's fine. It's when I start looking at, can you stop doing that? Get off of that. Thank you. If I do a vertical line like this, well, now I'm going through two different points, and so that makes it not a function. So just know this is not a function. But even though it's not a function, we still want to talk about what would be the domain and range. So we can kind of see, kind of lightly here, where you've got the x and the y axes. So I'm grabbing this from Desmos. So the thing to notice here is that each square that we see is measuring half a unit. So here's what we want to do. We want to see what is our domain. And really, if you just take this farthest point here on the left and you bring this down to the x-axis like that, and you'd use everything going all the way over here to the right, which brings it down to this. So everything between these two values, okay, these outermost edges, that's going to describe our domain. So we see all the way out here at this point, this is when x is -7, and all the way here to the right, this is when x equals +1. So my domain will be the interval notation from bracket -7 to +1 with a bracket. So for domain and range, it doesn't really matter where do you cross the x or the y axis. That's not what's important. What's important is what values are being used for the x and for the y to make up this picture. So we don't need anything going beyond -7 or +1. Everything in between there is going to give us all those points that we see there on the graph. Now look at your y values. You see that the lowest we get is going to be coming from this low point here at the bottom. And so this happens here at -3. And this graph curves and it goes all the way up to this maximum point, which would be when y equals 5. So if you were to kind of map all of these points back onto the y-axis, you would have this. And so you want to translate what you see here on the y-axis into your range. Now, we're always doing these guys in interval notation. So with interval notation, you want to go from left to right, but you want to go from least to greatest as well. So when you're doing the x left to right, super easy. When it comes to the y values, the least to greatest is going to be bottom to top. So we're coming from a value of -3, and we go up to a value of +5. And we are including both of those. So there you have it. That's how we would find the domain and range for that particular graph. Now, where are you? Let me change this up. Yeah, I'm actually going to do this. That's going to be better for me. All right. So if I have, let's see. Oh, yeah, I want that. Actually, I want this. Yeah. Actually, hold on. Just to make it look even more fun. And now I'm going to do this. All right. Copy. Come on, mouse, where are you? All right. That's not what I'm trying to do. Goodness gracious. Again, I do not know why my dog must bark every time she hears the neighbors take out the trash cans. Anyway, let's look at this guy. Does this represent a function? Let's see. No matter where I put, no matter where I put a vertical line, I hope that you can see that it's going to be fine. There won't be any issues. Whether I do the vertical line here or here, no matter where I draw it, I'm only ever going to be touching this graph in at most one spot. So for this, we can say that yes, this is a function. Now let's talk about the domain. You see that as I go from left to right, there are no There are no gaps, there are no jumps, and there are no places where the graph seems to all of a sudden stop. So as you trace along from left to right, you'd have to be including everything. That's not where I'm supposed to be. Sorry. You have to be including everything here on that x-axis. So everything from left to right. And again, don't get bogged down looking at, oh, well, I got to just put the points where it touches the x-axis. That's not what the domain says. The domain is all of the x values that are used to make up this picture. So it's not just this point right here and then this point. It's all of these points in between, and there are an infinite number of them. And it just keeps on going left and right. So you see that, this point goes down to here and here. This one goes up here, and so on. So we need all of these guys. So my domain will be all real numbers. So we can say negative infinity to infinity, or you can use this funny looking R symbol to represent the set of all real numbers. Now, what about your range? Does your range also go from negative infinity to positive infinity? Or does it have some kind of boundary? If you look at this, it seems like the lowest I get is right here. And that seems to be pretty consistent as you go all across the graph from left to right. So it seems to be that this is as low down as I go. And then this goes all the way up until you get to about right here. And that's where it seems to stop. That's the ceiling for it. And so what you see here, what I've graphed is really what your range is. But we then have to pull that information from the graph so that we get the right values. Again, keep in mind that we are dealing with each square being half a unit. So this is 0, so this is going to make this -1 down here. So we see this is 2, 4, and this is going to be 5 up here. So my range is going from -1 up to +5. And that's really all there is to do for that one. Now, let me do another one. Let's see, is there... Yeah, I know I didn't want to do that. That's not what I want. Okay. So let me do this guy. Actually, I need to change that. Oh, don't do that. Oh my gosh, what am I doing? Oh, that's better. Okay, and now let me do this. All right. Do a little bit of resizing here so it fits better. All right. Let's look at this one. What we have is, well, it's a vertical line. Now, it's not really showing it on here, but it would be continuing from the top to the bottom. You're going both directions there. So the big question here is this a function? Well, if I were to try to draw vertical lines, I'm okay here. I don't cross it in more than one spot. Here is fine, here is fine. But if I get right here, I'm actually on that line. I'm intersecting it an infinite number of times. So that means that this is not a function. Okay, so it's not a function. But what about the domain? What can we say about that? Now remember, the domain is the set of x values that are being used in this graph, right? So we see that this is the graph for the equation x equals 4. And if you look at this, every place that's on here It's just x equals 4. So that is the only x value that is being used by this relation. Nothing else. Now, a lot of students sometimes get confused and they say, oh, from 4 to infinity. But if you were to say that for the domain, that means you're talking about 4 and going all the way out to the right. But we're not, right? Here, it's just 4. And since that is a discrete value and that is the only value, we're going to use these braces here for the set notation and just write 4. So that's my domain. And that's all there is. Now, if you were to think about your range, so think about this being on your y-axis. You see that we're going all the way down, and this graph goes all the way up, and there's no gap and there's no break to it, so it's including all of the pieces there on the y-axis. So because of that, your range would be all real numbers. But this is most assuredly not a function. Okay? All right, let me do another one. Gotta make sure this is a good one for you. If I do this and that, let's see. I'm gonna do this and that, and then yeah. I just need to grab this for you. Do this. All right, let's see. There we go. That looks nice. All right, so let's look at this graph. Is this representative of a function? Well, if we do the vertical line test, right, you'll see that the vertical line is fine here and here and here. Now it looks kind of iffy the closer I get to this particular x value down here, but I'm going to let you know that if we were to zoom in, this is going to be a function. In fact, what this graph is doing is that he's going to come to a clear point here and here at the bottoms, but he is going to be like opening up and out if you were to keep zooming out of this graph. But this is going to pass the vertical line test. So yes, this is a function. Well, how do we talk about the domain? Well, if I were to look at this on my x-axis, you've got this point here on the left that starts right here at -3, and then it's everything going here to the left. So we need that particular section of the x values. And then there's this jump, there's this gap where we come back over here at this x value of 2, and then you need everything that's to the right of 2 to be used to make up that picture. So my domain is made up of 2 parts. It's made up of the left part, so -infinity to -3, bracket. Then we use that union symbol, and we join it up with the other piece from 2 to infinity. And that's our domain. And we had to break it up because it's not connected. Anytime you have like a jump or a gap, you want to be very careful about how do we describe the domain and range. Now for the range, if you were to look at what's here on the left, and if you were to kind of map this over here to the y-axis, this guy is coming from -2, and you see that he goes all the way up to infinity without stopping. And if you look at the right part, he also starts down here at -2 and goes all the way up. So even though these pieces are disconnected, there is that overlap that you see there with the range. And so for the range, you describe simply what you have colored on that y-axis. So going from a bottom of -2 up to infinity. That's how we would describe the range. So really, no matter what picture we have, it shouldn't be that difficult for us to identify the domain in the range, as long as we can correctly map it to the x and the y axes. Now, that's the difference between having something that's a function like this, or having something that's just a relation. Of course, this guy was a function, and this first guy here was not a function. Now, this second graph that we did, if we had turned it on its side and it was kind of going back and forth like that, well, now all of a sudden it would fail the vertical line test, because as it goes back and forth, it'd be crossing a vertical line an infinite number of times. But the way that we have it here, it does pass the vertical line test, so that's what made it a function. All right, so let's really get into function notation. All you need to know how to do is to add, subtract, multiply, and divide. And make sure you can read algebraic symbols. All right, so I just want to go back to the basics here. If I said y equals 2x plus 5, and so what we've seen before is that I could create a t-table of values, and I can say, you know what, if x is equal to 3, what is the corresponding y value? And the way you would do that is that you would say, okay, so that means y equals 2, I'll replace the x by 3, and then I add 5, and I just follow the order of operations. So that's 6 plus 5, which equals 11. Okay, that's all that we're doing. And so you finish off this ordered pair, and you say this is the ordered pair 3, 11. Now, when we have y by itself like this, we're going to see that we can start to exchange y for our function notation, which we use f of x. So make sure that you are reading this correctly. Don't say fx. This is read as f of x. F is the name of the function. X is the variable that the function depends on. So as x changes, that's going to tell you what the output value is going to be. So before, when I said y equals 2x plus 5, we're going to start transitioning into using the function notation. And for this one, I'm going to say f of x equals 2x plus 5. All that means is that when we change this x to an actual value, we change every x that we see in that expression, and then we do the order of operations. That is all that it means. Now, one of the things I'm really going to harp on here is making sure that we use correct function notation. So you might see problems that say this. It'll say evaluate, and maybe it says find. And suppose it says find f of 3. Well, since this is my input value, that's what I'm plugging into the function, every place that I see x, I'm going to replace that with 3. Now, here's what I tell my students. Anytime you're doing this kind of substitution, always use parentheses. Also be neat when you write this, because I see students every semester that they know what they're doing, but they're going way too fast, and they don't translate the symbols, they don't translate their signs from one line to the next correctly. And so they get off. Get off by a negative, off by many factors, so just be careful. So I'm going to say 2, I'm going to use x I'm going to replace my x with parentheses, and inside the parentheses, I'm going to plug in this given value of 3. So this is what f of 3 means. Replace your variable x with the input value of 3, and then do the math. Now notice I'm not saying f of x equals anymore. I'm asking you to evaluate f of 3. So x is gone, and he's been replaced with 3. And now we do the math. So that's 6 plus 5, and that equals 11. So pay attention to what we did. Our input was 3. The output was 11. We're not solving for anything here. We're simply plugging things in and getting something out. It's the same way that functions work in the real world. For example, if you were to go to a vending machine, your input is the button combination that you press to get your bag of Flaming Hot Cheetos or to get your Coke or your Sprite or whatever it is. Here, our input is 3. And what we're getting out of this particular machine is that we're getting 11 out of it. Now, we don't always write this as input equals 3 and output equals 11. A lot of times we use an ordered pair. And we say, oh, we plugged in 3 and we got out 11. And if you were to keep plugging in, numbers over and over again, you're going to get a bunch of these ordered pairs. And collectively, they will form the picture that is the representation for this function. Now, since this is a function, since I'm using this function notation, that means that the visual representation, the graph of this, will pass the vertical line test. In other words, you plug in one value, you get out one value. That's what it means to be a function. Now, we could do this again and say, I don't want to go too far for this. Let's get rid of this real quick. So if I ask you to do f of -10, still using the same function, so the f refers back to my function called f, and -10 is now my input. So we do 2 times -10 plus 5, and then what you do the rest of the way, you're not solving, because solving means you're trying to find a replacement of the variable that makes some equation true. So you're not solving, you are evaluating. This is an expression. You simplify. So you do the order of operations. So we have -20 plus 5, and we get -15. So in this example, we plugged in -10, and we got out -15. So that would complete the ordered pair. If you looked back at the very beginning here when we said y equals 2x plus 5, if you plug in -10, you would get -15 from that linear equation. But now we're using function notation, which is why things look just a little bit different. But the thing is, it doesn't matter what this looks like. We can make things big and bad, it's still going to work the same. So suppose I give you this new function. I say g of x is equal to 2x squared minus 7x minus 3. So new function, new name, we're going to use g. And we see here that, again, x is my input value, and so anything I plug into the function is going to get plugged into where I see my variable x. So if the problem says to find or evaluate, and kind of use those interchangeably, and we say g of -4. Well, it is as simple as taking this expression, and any place that we have x, we're going to rewrite that with parentheses. So it's going to be 2, and instead of x squared, it's parentheses squared, minus 7 times parentheses minus 3. This is my input value. That's the guy that gets plugged into all of these open parentheses. So I'm going to put -4 here and over here. So doing that is the first step in understanding how do we work with functions. The rest of this is order of operations. What do we do first? Well, powers happen first. Notice that the square in the original expression was only connected to the x, not the 2. So here the square is connected to -4, so we have to evaluate that first. So that's 2. The -4 squared becomes positive 16. Let me just write the rest of this stuff down right now. And now we're going to go through and do the multiplication. So 2 times 16 is 32. -7 times -4 is plus 28. And then we have -3. So finish, combine everything. 32 plus 28 is 60. 60 minus 3 is 57. So that's it. Again, nothing to solve. So at the very end, don't say, oh, so what does x equal? Well, just in case you didn't notice, x was negative 4. And we said, okay, we want x to be negative 4, so let's plug that in, and what do we get out? We get out this guy that is essentially my y value. You plug in the x value, you get out the y value. Right? And again, that's all there is to it. Now, when I put a problem like this on a test, the most common mistake that I see with my students is that they somehow do 2 times negative 4 first. They don't apply the power first like they're supposed to. Or they don't use parentheses well. Or maybe they say, oh, so negative 4 squared is negative 16. You know what? Hold on. I hope that you can all believe me when I say that negative 4 squared is not negative 16. However, if you were using a graphing or a scientific calculator, you might be convinced otherwise. Because a lot of students think that whatever they plug into their calculator, whatever they get out of it, it's infallible. It's always right. If you type negative 4 squared into a graphing or a scientific calculator, just like that, it will give you the answer, negative 16. Now, if that's what you meant, great, the answer is negative 16. But if you meant to say negative 4, that number is being squared. Well, then that gives you the different answer of positive 16. You might say, see, this is why math is stupid. No, this is why math has rules. This is why math has syntax, so that whenever I'm looking at an expression, I know exactly how to evaluate that. In the first expression, we have this square that is attached only to the 4, not the negative. So you've got 2 operations here. You've got the negative and you've got the square. The square would happen first, so you square 4 to get 16. And then you have this little after effect of the negative that shows up. As opposed to the second expression where it's negative 4 squared, where this means you have negative 4 times negative 4. So you're squaring not just the 4, but also the negative, which is why the result is a positive. Another common mistake that I see with my students is that they will put a negative 4 in that first set of parentheses, but then they forget that there's a negative on the 4 that they're plugging in on the second guy. And so you forget that sign, and that messes up everything else. So again, we have to be very, very careful about how we do this. So really, no matter what the expressions are, I'm just taking numbers and I'm plugging them in. Now, sometimes it's not just numbers. So if I define f of x to be, define this a little bit differently, I'm going to say this is negative 3x plus 7. Again, it's a function, and the function gives you a rule so that every time you plug in a number, you're going to get something out. You replace the x with that value, and you do the arithmetic. But this is a rule. So for this particular function, it says that whatever you plug into the function, it's going to multiply it times negative 3 and then add 7. Even if I do something like this, if I say, so then what's f of w? Well, you do negative 3, you do parentheses for where the x was, this is my input, and that's going to go where my x was, like that. So you can plug variables into a function. The function, again, is just a rule. So this becomes just negative 3w plus 7. Nothing really special. Now if I say, what is f of 2p minus 6? Well, this whole expression now is my input. So using the function f defined above, it's negative 3 parentheses plus 7. And so my input isn't a single number, but it is an expression. So we replace the x with that expression, and then we do the math. Well, really here it becomes algebra because we have variables. So we take the negative 3 and distribute. So we have negative 6p plus 18 plus 7. And so altogether we have negative 6p plus 25. Again, nothing to solve here. You just plugged in an expression and you actually got out another expression. Now if I'd plugged in a specific number, like 3 or 2/3, then I would get out just I would just get out a constant, right? But again, I just want you to see how we do functions. Whatever's inside the parentheses is what the variable gets replaced by, and then we just do the arithmetic or the algebra to finish. Now here's some fun things that we can do with functions. And this is called function operations. So this is when you're working with a couple of different functions. We can do our basic arithmetic operations on them. And so I want you to be familiar with the notation. If you have two functions f and g and you see this expression, f plus g of x, that means f of x plus g of x. In its simplest terms, that's all it is. That really shouldn't be that big of a stretch of the imagination. Now, the one thing we do have to be very careful about is that when we're talking about functions and function notation, we don't get to do things like distributing. Distributing is not something that happens when it comes to functions. So even though it looks like, oh, well, if we got f plus g and that's times x, but the thing is, that's not times x. In the context of functions, those parentheses next to each other does not mean multiplication. It means we're doing the functions f plus g of the variable x. If I do f minus g of x, that may be rewritten as f of x minus g of x. Again, that hopefully will make sense. If I have f, g right next to each other, here, this is how we would represent that we're doing multiplication with our two functions. So this means f of x times g of x. Again, intuition should take over and be like, oh, that makes total sense. If I have f over g of x, I bet you can figure this one out. That's going to be doing f of x divided by g of x. The one thing to watch out for here, because we're dealing with fractions, this is provided that your g of x function is not the zero polynomial. Because if g of x is equal to 0, like if that's just the way it's defined, basically like y equals 0, then you can't do the quotient of these two functions because you would have something that is perpetually undefined. All right, so now that we have that out of the way, let me show you how we go about using these. So if I start off with something like this, if I say f of x is equal to 5x minus 2, and I give you a second function, g of x is equal to negative 2x plus 3. Again, just two functions, nothing to be concerned about. And then I ask you this, and I say find or evaluate f plus g of 7. Now there's an easy way and a hard way of doing this. I would like to show you the easy way if you're willing to see it. So the easy way is to first rewrite this based on what we wrote at the top of this page. And rewriting this means that we have f of 7 plus g of 7. That is the easiest way to do this. So what you're doing is that you're turning one problem into two smaller problems. Now I'm going to do this. I'm going to let blue be for f and the pink B for G. The way I suggest you go about doing this is that you evaluate these two functions separately and do them off to the side. So I'm going to, off to the side, go f of 7. And that just means I'm going to do 5, replace the x by 7, minus 2, and just off on my own, I'm going to work that out. Now, g has no bearing on what I do here. This just says find f of 7, and that's what I'm going to do. So this gives me 35 minus 2, which equals 33. So then back over here, where I had f of 7, I'm now going to write 33. And then plus, I'm going to figure out what g of 7 is. All right, so g of 7 is negative 2 times x, which is 7, plus 3. So I do the arithmetic. That's negative 14 plus 3, and we get negative 11. So come back over here. This is negative 11, and then I just do the math that's here. 33 plus negative 11 gives me 22. So you evaluate these two functions individually, and then you bring them together according to what the notation says. This says f plus g, so you add the results. If I did something very similar to this, and instead I said, all right, what's f minus g, and let's still do f minus g, and let's do this of 7. So splitting this up means we have f of 7 minus g of 7. Well, I've got some good news for us. We already know what f of 7 and g of 7 are, because we did it over there, right? My suggestion is to use parentheses whenever you're plugging in these, or whenever you are writing these values. So f of 7 is still 33. G of 7 is negative 11, right? So I hope you can see the importance of using the parentheses when I do the substitution. There is subtraction that is part of this problem because it says f minus g of 7. So we got the negative there, but then I have the negative as part of that negative that negative 11 that result from g of 7. So this is 33 plus 11, so my final result here is 44. So again, we already have the work done off to the side. We brought those values together, first through addition, and now we're doing subtraction. Same thing would happen if I decided to do this. If I said f g of 7. That means f of 7 times g of 7. And again, we already know what these values are. So we have 33 for f of 7, we have negative 11 for g of 7, and then we just multiply these guys together. Now there's a fun trick for multiplying times 11. So the answer here is negative 363. What do you think? Hopefully not too bad. All right, so let me give you some new functions where we actually have to do some work here. So let's say f of x is equal to x squared plus 5, and g of x is equal to, let's say, 4x minus 9. So new functions, new definitions for f and g, so don't go back to the previous stuff. When I write f of x equals this, I'm giving you a new rule, a new definition for that function f, and also for g. So if I ask you to find g minus f of 6, order is going to be very important here, especially when we're talking about subtraction. So g minus f of 6 means g of 6 and f of 6, and then you subtract it in the order g minus f. So if I use the same coloring scheme as before, so here is g that's in pink, so g of 6 is going to be in pink, f is in blue, so f of 6 is going to be in blue. Alright, so I am going to do g of 6 first because that's the first thing that's listed. Alright, so g of 6 is 4 times 6 minus 9. Take your time, show each step. That way, if you get something wrong, it's easier to go back and figure out where the mistake happened. Alright, so this is going to equal, let's go ahead and get this set up for success. We have 15 in here, and then we're going to figure out f of 6. So this means I'm going to do 6 squared plus 5. So we get 36 plus 5, which equals 41. So we evaluated the two functions separately, and now we bring the answers together according to the steps that are here. 15 minus 41 is negative 26. And yeah, there's not anything else for us to do here. I mean, I could ask a follow-up question and say, okay, well that was g minus f. What if I do g f of 6? Well, when g and f are right next to each other like that, that means I would have g of 6 times f of 6. And again, we can pull those values from what we've already done. So we've got g of 6 is 15, f of 6 is 41, and then we multiply these guys together, and that should give us 615 if I've done the math correctly. Let's see, 600, yeah, 615. Of course, if I'm wrong, you guys will let me know in the comments, right? Yeah. All right, so that's function operations. Again, I don't think it's that bad. You've got two functions, and you just do the math that's there. You do them individually, and then you bring the answers together according to what it says, whether it's add, subtract, multiply, or divide. Now, let me show you the piece that tends to cause a lot of my students to stumble, and that's function composition. So function composition looks very similar to what we did with function operations, but it's not quite the same. You're going to see notation that looks like this. F, a little open circle, g, and then of x. So the way that we read this as f of g of x. So we write that, literally what I'm saying, f of g of x. So essentially what you're doing is that you're taking one function and you're kind of stuffing it inside of another function. I refer to this as a mathematical turducken. If you guys used to watch, if you watch like, NFL games on Thanksgiving, especially when you had John Madden and Pat Summerall on, they would always have this little feast with a turducken, which was a chicken stuffed inside of a duck, which was stuffed inside of a turkey. Please don't ask me about the logistics of how you actually do that. I don't know. But that's kind of what this is to me. You've got some input x, and you're going to stuff that inside of g, and you're going to take that result and you're going to stuff that inside of f. So the difference here is that you don't go off to the side and figure out what is f and what is g of that same value. No. One function gets evaluated first, and then you pass that new number to the next guy. So you have to kind of wait your turn. I also think about this as an assembly line, right? people, robots, whatever it is, they have different functions that they do. Functions, get it? So something comes down the assembly line, and maybe your job is to, put things in groups of 4. And the next person puts them in a box. So you've got to do things in a particular order or things get messed up, right? If you swap those orders around, somebody puts something in a box, they don't have anything, but then you just kind of group boxes and, yeah. So order is very important when it comes to evaluating. So if I say f of x is equal to, let's see, 5x minus 1, and g of x is equal to negative 2x plus 9. And if I say to find or evaluate f of g of 2. 2 does not get to go into both of these functions. This notation means that you would do f of g of 2. So the 2 goes through g first, and then it goes to f. Better example than the... No. I think another example I was using this semester for function composition, being that there's a particular order to things, it's like, it's like your digestive system, right? So, like I'm putting 2 into G, it's in my mouth, I'm chewing that up. It changes the content, changes the chemical composition of it by the time it gets to my stomach, so it's something different. So I'm not putting the exact same thing in my mouth and my stomach. There's a process for that, an assembly line. All right, so again, here's this. I'm going to figure out that guy first, and then I've got this. All right, so let's do this. Off to the side, I'm going to figure out g of 2. All right, so that's negative 2 times 2 plus 9. Again, this goes back to what we were seeing pages ago. Plug in the number, do the arithmetic. You are not solving. So you get negative 4 plus 9, and you get 5. So F has been waiting for G to finish up whatever he's doing with the 2. And G says, all right, bruv, I'm done. Here, you get 5. So F doesn't see 2. F sees what G has done to 2. And now we figure out what is f of 5. So we use the correct function, f of x. Again, this is why I like to use colors. So that's 5 times 5 minus 1. So 25 minus 1 equals 24. So the end result is 24. Now, what do you think would happen if we were to swap the position of G and F? Would it make a difference? Typically it does. So if I were to just swap these positions and I did G of F of 2, that means that the order is changing, and so I have to do F of 2 first, and then I'm going to plug that result into G. So G is the one who's waiting this time. All right, so let's go up to the side and figure that one out. So F of 2 is 5x, so x is replaced by 2, minus 1. So 10 minus 1 is 9. So now we're doing G of 9. All right, now let's go up to the side and figure out what is G of 9. So G of 9 equals, you know what? I forgot what G was. Negative 2x plus 9. All right, so I'm making a little note here. G of x equals negative 2x plus 9. Okay, just to make sure I have my function, basically my formula, so I can plug in correctly. So negative 2 times input value of 9 plus 9. All right, so we get negative 18 plus 9, which equals negative 9. All right. So one way, we get -9. Another way, we got 24. So the order that we evaluate these functions in does matter because it's function composition. Okay. You know what? Let's see what happens, because you might see notation that looks like this. If you have to do g of -13. So basically you're taking g, you're going to evaluate -13 into g, and then you'll have to take that result and plug it back into g. So it's nested inside of itself. It's very similar to if you had the square root of a square root. All right, so I'm going to do this off to the side. So g of -13, -2 times -13 plus 9. So 26 plus 9 equals 35. So again, as long as we know arithmetic, we're going to be fine. Well, it's knowing arithmetic and knowing how to interpret the symbols that we see here. So this becomes g of, well, g of -13 we see off to the side here becomes 35. And now we figure out g of 35. So we plug it back into itself. So -2 times 35 plus 9. So -70 plus 9 equals -61. There we go. So it does come down to making sure we understand how to evaluate functions. And then how do we evaluate when we got this function composition, right? There is the order that we have to pay attention to. So g of -13. -13 goes into g. It does whatever. And then you put it back into it. In the previous example, we figured out, we had g of f of 2, so 2 goes into f first. F of 2 becomes 9, and then we plug that into our function g. And you can keep nesting these guys over and over again. You could have, f of g of h. You could have 3 nested functions. But it's important for us to know how functions are kind of inserted inside of other functions for something that you'll see later on in calculus. So we could talk about the chain rule. It's actually not too bad. All right, let me check something real quick. I just want to make sure that I am on the, and of course, I want to make sure that I'm on the right track for what I wanted to talk about today in terms of the content. All right, let's see. In here and here. Okay. All right. Cool. Cool. All right. So I am going to come back over here. I'm going to grab this. All right. So the last bit of stuff that I want to talk about today will be parent functions. And these are, we're just going to be talking about some basic shapes of functions. Some things are going to be non-linear even. And we want to talk about what are the key characteristics, because we need to have this information so that tomorrow, when we talk about graphing non-linear functions and function transformations, things are going to be a lot easier for us. So starting with just your basic linear function. So your basic linear function is this. F of x is equal to x. I mean, that's nothing more than just saying y equals x. A lot of times what we'll do, though, is that we will consider just a few ordered pairs to try to get a good idea about the shape of this graph. And so for a lot of these graphs, a lot of these functions, we'll just kind of go with this default -2, -1, 0, 1, and 2. And we just kind of plug that in. Now, if this is a linear function, and really, I guess we could say this is the identity function. The identity function meaning what you plug in is exactly what you get out. So you plug in -2, you get out -2. Plug in -1, you get -1. 0 gets you 0, 1 gets you 1, and so on. So when you plot these points, you would have a graph that starts off looking like this. And if you keep going, you'll see that because this is a linear function and it's understood to have a slope of 1, that these are going to be your key points, going all the way up and to the right and down and to the left. And then we see that we do have a line, so let's draw a nice, hopefully a nice straight line, as long as this is going to work out well for me. Let's see. All right. Now, all these guys are going to be functions, which means they're going to pass the vertical line test. But we want to talk about the domain and the range. So the domain for this function is going to be all real numbers, meaning there won't be anything that's going to be a restriction for what we can plug into this guy. And for most of the things we're going to see, your domain is going to be all real numbers. Unless you run into, at least right now, one of two situations. If you have a square root in your function, that can limit your domain. Also, if you have x in the denominator of a function, that can also limit your domain. My range, as you go from bottom to top, you see that you would be including everything. So there's no low point here, there's no high point. It just goes on and on forever and ever. So that is your linear function, which in this case is more precisely your identity function. Let's look at the next parent function that we have. The next parent function is called the squaring function. Now, the squaring function does exactly what you would expect it to do. It takes every input and it squares it, which is why it's f of x equals x squared. So just like we did above, if I just do a t-table of values to get an idea about what's going on here, and I plug in -2, -1, 0, 1, and 2. Again, the squaring function does exactly what the name suggests. It squares your inputs. So if you square -2, you get +2. No, you don't. I don't know where I am. If you square -2, you get +4. You square -1, you get +1. Then you get 0, 1, and 4. So now if we plot these points, -2, +4, -1, 1, 0, 0, 1, 1, and 2, 4. So we start to see that the shape is definitely not a line. And in fact, if we were to go one step further here, we would try to plug in 3. 3 squared gives us 9, so it'd be all the way up here. And you'd actually have a similar point there on the left side. So for a squaring function, we end up with this kind of shape. Please make sure that you are drawing a nice, smooth curve. So the shape of this guy is called a parabola. And with the parabola, we have certain key features here. We have this point that's here at the very bottom, this minimum point, called the vertex. Now, I think it's tomorrow. Yeah, so tomorrow we'll be spending a bit of time talking about just quadratic functions in general and how you would ever go about finding the vertex, no matter what it looks like. And then you have this imaginary line that goes right through the center of this, or through the middle of this, and this would be your axis or your line of symmetry. So just some key things to know here. Now, what we're going to do eventually is we're going to be taking all the shapes that we're talking about, and we're just going to be moving them around. talking about how you would translate things up, down, left, and right, how you might flip it upside down, or stretch it or compress it. Let's talk about the domain. Remember, the domain is, as you go from left to right, what are we including here? And if you look at this, it should be all real numbers. There's never a place here where this squaring function cannot accept a number. So we said already there were two things to watch out for that can restrict the domain. One of those being a square root, which we don't have. The other being x in the denominator, which again we don't have. So yeah, any value is going to be good to plug into this. Now your range though. Your range is going to be the set of y values, and we look at that going from bottom to top. So from the bottom, we don't have anything until we get right there to that vertex. And that is a y value of 0. And then the graph goes up toward infinity. Now, I know this is kind of curved when it hits the vertex, but you are including that value of 0. Like you see it being used right here. So that guy gets a bracket, and of course we always do parentheses for infinity. Now, there's another aspect to this that we want to talk about. So a lot of times in the textbook, it may ask you to find the intervals of the domain over which your function is increasing or decreasing. So when we talk about increasing, we're talking about as x gets bigger, y gets bigger. In other words, if you were to trace from left to right, the graph is going up. Decreasing on a function means that as your x's increase, the y decreases. In other words, as I go from left to right, the graph is going down. So here on this particular graph, you see that we are decreasing here as I go from left to right. Now some students may argue with me and say, but you've got the arrow pointing up there on the on the left. Yes, because the arrow pointing up on the left is to signify that the graph is continuing on in that same kind of pattern as it leaves the graphing grid. But as I trace from left to right, my graph is decreasing. Then he hits the vertex, and then he's going to be increasing. He starts to go up from left to right. So the way that we're going to describe this, at least the way I like to show it, is I'm just going to, kind of like a shorthand, I'm just going to say this. So we are increasing on the interval from 0 to infinity, and we are decreasing on the interval from negative infinity to 0. And again, this is as you are moving from left to right. So from left to right, you're going down until you get to an x value of 0. And then beyond that, for any value of x greater than 0, if you have two x's that you're comparing, where one is bigger than the other, if you're increasing, that means from one x to the next, your y value has increased. So we always look at this from left to right. And again, you can just trace your finger along here, right? I'm going down, and then I'm going up from left to right. And when we do these little intervals here, you're doing this in terms of your domain. So what intervals of your domain will cause you to be increasing or decreasing? That's all it is. Now, if we were to apply that back here on just your regular identity function, this would say that you were increasing everywhere. Because as you go from left to right, you are going up the whole time. So then you would say that you are decreasing nowhere. So just some things to keep in mind whenever you are maybe coming across these problems in the homework, or you see them elsewhere and you're trying to figure out what does it mean when you're increasing and decreasing. Exactly what I was showing you. All right, so let's look at your absolute value function. So the absolute value function is just the absolute value of x. So every value that you plug in here, it's just going to spit out the absolute value of it. In other words, what is its distance from 0? So if I plug in -2, the absolute value of -2 is +2. Absolute value of -1 is +1. Plug in 0, you get 0. Plug in 1, you get 1. You plug in 2, you get 2. So no matter what you plug in there, you're always going to get something that's non-negative. If I if I plot these points, -2, +2, -1, 1, 0, 0, 1, 1, 2, 2. If you kept on going with this, the absolute value of 3 is 3, the absolute value of 4 is 4, and so on. So you would have all of these points there on the right side. And you'd have something very similar here on the left side. So if I plug in -9, I get +9. One of the things I really like about the absolute value function is that it's made up of straight pieces. So it's very easy for us to graph. We get to use a straight edge. And we get something nice like that. Now there are some similarities between the absolute value function excuse me, and the squaring function. The absolute value function also has a vertex. And just like the parabola, it has an axis of symmetry. We can talk about its domain. I think the domain should be fairly straightforward because you see it goes all the way left, all the way right, so that's going to be all real numbers. The range is going to be very similar to the parabola. The lowest the graph gets is that y value is 0, but then it just goes up. So including 0, so bracket on 0 to infinity. All right, well, let's talk about where are we increasing and where are we decreasing. As I trace along from left to right, you'll see that I'm going down here on the left, and then after the vertex from left to right, I'm going up. So you're going to see something very similar as we did for the quadratic. You're increasing over the interval from 0 to infinity, and you're decreasing on the interval from -infinity to 0. And yes, we will keep parentheses on the 0, because typically what you're going to see is the question will ask over or on what open intervals of the domain. So it means they're going to be open or parentheses on both ends. Yeah, and we'll be talking a lot more about these absolute value functions tomorrow. No, I didn't want to do that. Let me this. So let's talk about the cubing function. The cubing function, again, does exactly what it says. It takes every input and it's going to cube it. So you'll see something that seems kind of similar to the squaring function, but just a little bit different because we're cubing things. So let's plug in our usual suspects, -2, -1, 0, and 2. So if I cube -2, so we got to be careful. Because you're cubing a negative, the result will be negative. And 2 to the third is 8. If I cube -1, I get -1. Cubing 0 is 0, 1 to the third is 1, and 2 to the third is 8. So when I plot these points, I've got -2, -8 down there, -1, -1, 0, 0, 1, 1, and 2, 8. Now, students oftentimes try as hard as they can to make this a straight line. It's not. Something that helps me is to kind of exaggerate right here in the middle. This is going to be flat. Wait, where did that go? So it's going to be kind of flat right there, and then it's going to curve up to go through these points. It's almost like you're doing kind of like half of a parabola over here. And then you're going to do the same thing, but like rotating this 180 degrees. And so you're going to be curving down as you go through these points. The thing to be very careful about here is that for these guys, they're never going to like curve out. So over here on this last page, when we had the squaring function, this guy keeps opening up and it keeps getting steeper and steeper. He never opens out like it's the top of a flower or anything. So make sure these guys keep getting steeper and steeper as you go off there. Now it's never going to be completely vertical. It may look like that, but it never is truly vertical, because if it were vertical, it would fail the vertical line test and it wouldn't be a function. But what about the domain? Again, we don't have any radicals, no square roots. We don't have any denominators with x, so my domain should be all real numbers. Now what about the range? As we go from bottom to top, you see that we are including everything. This graph goes all the way down. He goes all the way up. No breaks, no gaps. So the range is also all real numbers. But now let's talk about increasing and decreasing. If I were to take my finger and trace along this graph, what's going on? I hope that you can see that here on the left side you are going up, and you're still going up from left to right. So you are increasing over the entire domain from negative infinity to infinity, but you're decreasing nowhere. Yep. So that's the cubing function. Now let's talk about a function that is very closely related to the cubing function. And that is going to be the cube root function. Now, something that we'll be talking about, I think on Friday, will be inverse functions. So you'll hear me talk about this guy again. Now, the cube root function is f of x is equal to the cube root of x. I know, shocking, right? Now, I don't want to just plug in any numbers that I can think of in here. I want to plug in numbers that are going to work out nicely with the cube root. That means we want to plug in numbers that are perfect cubes. So previously, when I was cubing things, please hold. Sorry about that. My wife letting me know that she's on her way home. She was just volunteering at a pet adoption event. We got 7 pets adopted out. So 3 cats and 4 dogs. So really good numbers. Let me just make sure that I remind everybody out there that pets should not be presents. Like, don't say, oh, I'm going to buy this pet as a present. That's really not the best way to go about getting a pet. But anyway, it's a good day. So she was doing that while I was grading tests. It all works out nicely. But anyway, for the cubing function, you see that these numbers that we have out here, these are all perfect cubes. So we want to use these guys to build our t-table, what we're going to plug in here. So we plug in -8, -1, 0, 1, and 8. When I do the cube root of these, I'm going to get my answers. And since these are nice cubes, the y value is going to be a nice number. So The cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Then we have 0, 1, and 2. So, plotting these points is going to look very similar to what we had for the cubing function. But all these order pairs are flipped around. So here they are. Now the shape here can be a difficult one to graph. So remember back over here for the cubing function, right there at the origin, it was kind of flat, right? Well, if you kind of flip that around, we're going to be kind of vertical right here like that. And then we're going to curve out. So it's almost like we have a cubing function that's turned on its side. And then I'm going to curve down and to the left over here to get the left half of that. Again, it's the graphing of these guys is something that just kind of takes practice. And take your time, do a nice sketch, but just keep working at it. It's not always going to be perfect, but don't quit. Now your domain. Hopefully you can see the way this guy stretches from left to right. That domain is going to be all real numbers. The range might be a little bit more difficult for you to grab from this graph, but you'll notice that even though it looks like it's flattening out as I go to the right, this graph is still getting higher and higher. It's just increasing at a much slower rate than what we had here for the cubing function. But nevertheless, it's still increasing. So the range is going to be all real numbers. Well, what about increasing and decreasing? Well, as you go from left to right, just trace your finger along this. As I trace my finger along this, you see that I'm going up and up all the time. So it means I am increasing over the entire domain from negative infinity to infinity, but this basic graph is decreasing nowhere. All right, that's the cube root function. Now, last but certainly not least is our square root function. So the square root function is f of x is equal to the square root of x. Now, similar to what we had for the cubing function, we want to be very selective about our choices for input values. Now, since we have a square root here, that means we will have, or there's a possibility that we do have, a restriction on the domain. Because when we're graphing on this graphing grid, this is the grid for the real xy plane. So we won't be able to graph complex numbers on here. So nothing with the imaginary unit. We're not going to be able to see that here on the graph. So don't plug in negative numbers, because it's going to give you something that is non-real, which, yes, we've had solutions that are non-real, but in terms of graphing, we don't want to mess with that. If I plug in 0, square root of 0, 0, no big deal. Plug in 1, square root of 1 is 1. Now I don't want to plug in 2, because the square root of 2 is not a nice number. But the next nice number to plug into the square root function is 4, because that's a perfect square, and the square root of 4 is 2. And then the next good number is 9, because the square root of 9 is 3. Now, a lot of times students try to plug in 6. I'm like, okay, what's the square root of 6? It's not 3. So if I take these values, we get 0, 0, 1, 1, 4, 2, 9, 3. On the right side here, it's going to have a curve that's very similar to what we saw for the cube root function up above, but it's not going to be quite as flat. I mean, the differences there may be imperceptible, but yeah. So right now we can see that our domain is not all real numbers. Our domain is from 0 to infinity. A bracket on the 0 because we see that we do have that starting point there at the origin, 0, 0. My range is going to be very similar from 0 to infinity because the lowest point we get is there at the origin, and this guy just goes up and up and up forever and ever toward infinity. All right. So So that is your square root function. Now, just to kind of give you kind of a preview of what's going to happen tomorrow, is I'm going to take all of these parent functions that we were talking about, and I'm going to just grab the shape and move it around. And then once I move it around, I'm going to rebuild that. For example, just suppose that the starting point for your square root function was there, right? Suppose it starts here at -7, +2. And again, you're going to see me do this tomorrow as well. I pretend that this is my new origin, and then I reconstruct my square root function from this guy. So all those values in the t-table, I'm going to translate and copy them over here. So that's 0, 1, 2, 3, 4 was the next good number to plug in, 5, 6, 7, 8, and then 9. So what I'll ask tomorrow is, okay, what's the square root of 0? 0, which is why it's exactly there. What's the square root of 1? 1, so you're going to be up 1 from that new horizontal line. The square root of 4 is 2. The square root of 9 is 3. And so we'll take all of the stuff that we'd already graphed, and we just shift it over a little bit until you have a graph that looks kind of like this. Right? And so I'm going to show you tomorrow how there are going to be different numbers in different positions inside the functions that'll tell you how do we get there. Now, spoilers for this. This would be the graph of the square root of x plus 7 plus 2. And so the 7 inside the square root is going to react differently to the square root shape and its position than the 2 on the outside does. So we'll talk about, what do they mean, and how do I take my graph and move it around. All right, so it's a good place to stop right there. So I hope that you'll come back and join me tomorrow as we start talking about graphing these nonlinear functions, something that I feel like a lot of students struggle with. And I try to make it as super easy as possible, right? Because what we don't need to do is that we don't need to spend a lot of time plugging numbers into a function and doing the math. We can take the basic shapes and just grab them and move them around based on the numbers that we see in the function. So, until next time, everyone, have yourselves a great day. And as the kids would say, peace out.